All right, in this video, we're going to go over how to change the rules of exponents into rules for logarithms in base E, since this is for calculus. All right, so let's start with some givens. All right, in order to accomplish this, okay, I'm going to start with the following relationships. We're going to be given that capital A is E raised to the lower a. Okay, and capital B is E raised to the little b, right? This would give us the logarithmic relationships that the natural log of A is little a, and the natural log of B is little b. So we're going to be using these relationships throughout the video, all right? So for some number little a, e to the a will equal some other number. If you exponentiate little a, you'll get a value for big A by putting it in your calculator. Conversely, if you have a value for big A, you could find a value for little a by taking the natural log of it. So these could represent actual numbers. They just generically could be any number. We'll assume they're all positive numbers at this point, so that because exponentials have to be positive. And you can't take logarithms of negative numbers. So continuing on, we first want to turn the multiplication rule for exponents into a multiplication rule for logarithms. Okay, so you should be familiar with the fact that if I had e to the a times e to the b, the rules of logarithms say, rules of exponents say that we should make that e to the a plus b. You have a factors of e and b factors of e, so you end up with a plus b factors of e. Assuming you know that, then what we could do is we can turn that into a rule for logarithms, right? We can say that the natural log of capital A, capital B, big A, big B, okay, should equal the natural log of e to the little a times e to the little b. So we're subbing in for capital A and capital B. If we continue along that logic, we can say this is the natural log of e to the a plus b. Well, since e is exponentiated to the a plus b power, when we take the log of it, we're just left with little a plus little b. But from our definitions above, little a is the natural log of big A, and little b is the natural log of big B. So we've created a new rule here. If I have the natural log of the product of AB, we can say it's the natural log of A plus the natural log of B. So that's our multiplication rule for exponents. Okay, now, how might this apply to calculus? Well, you could show that the natural log of 2x is the same as the natural log of 2 plus the natural log of x. Using a chain rule, if we want to take the derivative of both sides, we could say that the derivative of natural log of 2x is 2 times 1 over 2x. All right, natural log of 2 is 0, and the derivative of ln of x is 1 over x. Well, you can quickly see that 1 over x is equal to 1 over x, so it does work out. Okay, so we can take derivatives of products by separating it into two terms or by using the chain rule. Now, let's move on to the division rule. So here's my division rule. If I'm working with exponents, I would look like e to the a over e to the b. Okay, and that gives us e to the a minus b. So following the same pattern as before, we can say, well, what is the natural log of capital A divided by capital B? Well, that's ln of e to the a over e to the b, which is the natural log of e to the a minus b, which is just a minus b. And then filling back in, that's the natural log of big A minus the natural log of big B. So if I'm dividing A by B. So if I'm taking the log of a quotient, I can say it's the log of the numerator minus the log of the denominator. So we could do it for like a similar kind of relationship. This one's not as important in calculus as the one we're about to get to, but if I had, the natural log of x over 2, I could turn that into the natural log of x minus the natural log of 2, and we could do what we did before and ensure that the derivatives are in fact the same, whether you use a chain rule or break it into multiple terms. What we want to do now is the power rule. This is the one that matters the most. This is going to let us do logarithmic differentiation. Okay, so using the power rule, we could start with e to the a to an unknown power, okay, is going to equal e to the a times that power again. Actually, the power is going to be a number that would be given. Okay, so we have that relationship. Okay, now how does that apply to logarithms? We could say, well, what about the natural log of a to the p power? Well, that's the natural log of e to the a to the p, which we just determined is the natural log of e to the a times p. And so since we've exponentiated e to the a times p power, when we take the natural log of it, we just get a times p back again, which I'll rewrite as p times a. Okay, so now that can be rewritten as p times ln of big A, which is why I put the a second, reverse the order. So we can take the power and bring it to the front and turn our exponential relationship into a product. Okay, so this is the power rule, and we will use that a lot in calculus. Okay, so here are some examples where this could be really useful. Okay, these are ones where you could just use a chain rule to get the derivative, but we can rewrite this as 2 times ln of x, and we could use, we could take the derivative of that instead. We could have ln of 2 to the x. Okay, we could say, well, that's x times ln of 2. So we've turned it into a product. Moderately useful, but where this is extremely useful in calculus is if I have something like that. Okay, it's neither a power nor exponential, it's a combination of the two. So what do? Well, I turn it into x times ln of x. Okay, so ln of x to the x would be x times ln of x. So we have a product that we can work with, all right? Likewise, if we had more complicated things like ln of x raised to the square root of 1 minus x, we could say, well, that's the square root of 1 minus x times ln of x, all right? And we would actually then be able to use a product rule to get a derivative of that, okay? And so that will allow us to do logarithmic differentiation. But this rule of logarithms, the power rule, is essential to being able to do logarithmic differentiation.